In our previous session, we concluded that bipolar transistors are not like switches, or they are not switches, although they can be used as switches to a certain extent, but they amplify the current based on the base current. They can be used as switches to a certain extent, but they will always remain a semiconductor in the circuit. Now, they are very different from MOSFETs, and that's what we're going to take a look at today. Hello friends, welcome back to the bench. Today we're going to take a look at MOSFETs. For that reason, we're going to use the same simulation software, LT-Spice, but again, you can use any simulation software, it'll work exactly the same. Your results will be exact same. Now, MOSFET is, what is MOSFET? Well, the name stands for metal oxide field effect transistor. Now, very important that it's a field effect transistor. It doesn't have to be metal oxide. All of those are FETs, field effect transistors. They are very much different from bipolar transistors because they don't operate on current. They operate on the potential. That's why they're called field effect. The electrical field is what controls the flow, not the current. Just like in bipolar transistors, we have collector, emitter, and the base. In MOSFETs, it works pretty much the same way, but we call, instead of collector, we call it drain. Instead of emitter, we call it source. And instead of base, we call it gate. Now, let's take a look at the first example, which is very similar to the example we had before of just single source of 12 volts, 100 ohm resistor, and a transistor cutting it to ground, which should give us 120 milliamps because it's 100 ohms on 12 volts. And we can see that it's almost exactly 112 milliamps, which means our transistor not only opened completely, but it creates nearly no resistance in the circuit, just like the relay switch would, right? So MOSFETs are very much like very fast switches, and that's their primary use. Now, the difference is, as I said before, we don't control the current, we control the voltage. Now, take a look what's happening here. We have, I called it a single side driver. The way it works is our source V1 generates square signal, 5 volts to 0 volts, right? The same way as we controlled the regular NPN transistor. And that's what we use over here. As the voltage goes to 5 volts on the base of our Q1, it opens and it delivers current to the gate of our MOSFET. The MOSFET we're using in this whole example and all of the examples following is IRF 7822, which is a relatively popular transistor for low voltages, relatively low currents, but you can do a lot with this transistor. Now, if we compare it to the current flowing through the resistor R1, we see that once it goes to 120 milliamps, it just stays there. It just keeps the transistor opened and it never closed. Now, why would that be? Let's check the voltage on the gate. First, it rises to about 1.5 volts, then in the second cycle to roughly 4.5 volts, and we have some tiny spikes, but for the most part, we have stable 4.5 volts on the transistor. So what's happening here? That is the first base property of the MOSFETs. The gate is kind of like a capacitor. You charge it to open the transistor, and to close the transistor, it's not enough to just cut the power to it, because that potential, that voltage, will remain on the gate of the transistor because it behaves like a capacitor. So we charged the gate and the gate never discharged, even though we stopped the current flow. And we can see that the current flow was only for this minute peak over here, right? Roughly maybe 0.5 microseconds. That is the time that was needed to charge the gate of the transistor, and it never goes down, right? Then we have pretty much zero current flow to the gate because the gate is charged. So that is important to know, and especially when you're measuring in circuit. Remember that if you touch the gate with your finger of the MOSFET, you can open it. You can charge the gate with just using your finger. And there is a great example that you can find on YouTube, connecting the MOSFET and touching the gate, and then touch the positive and negative. And you will see that the transistor will open as you touch the positive, and then if you touch the negative, the transistor will close. Now, resistance of our body is, I don't remember, some in mega ohms, a very big, very high resistance. But that's enough to charge and discharge the gate. So when measuring MOSFETs during the operation of the device, keep that in mind, because you can completely blow the device just by measuring the gate of the transistor of the MOSFET. Now, how do we fix this problem? We fix this problem by delivering a proper signal. In this case, we're delivering 0 and 5. So 0 meaning we're just touching the gate to the ground, right? We don't need the negative voltage in this case because it's the low transistor. And as we observe here, we have, and align it with the voltage, we have pulses of 5 volts, and the current on our resistor goes to 30 amps because it's 10 ohms on 300 volts. That's going to be 30 amps. And it goes to 0. Transistor closes correctly, right? It's perfect 0 and perfect 30 amps. Well, by perfect, I mean almost perfect, because one thing that we didn't have on our bipolar transistor, and I said that this parameter is not relevant, that's why it's not usually displayed on the data sheet, which is the resistance between collector and emitter. In this case, resistance between drain and source, we can see that it's 5 milliohms. In MOSFETs, that is important because MOSFETs are going to be driving loads, while the bipolar transistors usually not, and if they do drive loads, these are small loads, not a lot of current going through. The MOSFET is designed to work as a switch, which means in bipolar transistor we can use this range where transistor semi-opens, semi-closes, which causes a lot of power to dissipate on the transistor. But we can use that linear property of the transistor for amplification, for processing signals. We can use it for a lot of things. But MOSFET is designed to be just a switch. So what happens when you deliver a sine signal to the transistor, like so? If we align it with the current flowing through the resistor, we can see that our sine wave magically changes to the square wave. Now, why does that happen? We can see that if we zoom in to a single cycle, and our green line represents the voltage on the gate, while blue represents the current flowing through resistor R4. And we can see that as the voltage rises to about 2.5 volts on the gate, we have sudden switch. Suddenly, a lot of current is going to start flowing through the resistor. There is a little point of, you can see that it is linear in the range of like few hundred microseconds that the transistor takes to actually switch from being an obstacle to the current flow into being nearly a wire. We can see that the switch starts, or the process starts roughly when we have around 2 volts on the gate. That is 2 volts in reference to the source. We'll get to that in a second, because the same rule applies to MOSFETs as it does to bipolar transistors in reference to the voltage, or the voltage reference on the gate or on the base. So without using any complex components, we clearly transform a sinus wave into the beautiful square wave, just using the property of the transistor that switches nearly instantly from not connected to open, or from closed to open. And we can see that even because 30 amps is a lot, and it's a lot more than this transistor is capable of actually operating on, because it is limited to 30 volts. However, this is simulation software, so the simulation software doesn't really care about that. The transistor did not burn in this circuit, but in reality it would. In many circuits, especially on laptops or devices like that, maybe tablets, there's usually going to be 1 or 2 transistors that work as switches, basically kind of like a relay switches. And on power supplies you can have a physical relay switch, but on tablets, laptops, there's not enough room. So for that reason we use MOSFETs, and they don't work as switching elements, they just work as turn on, turn off, as relay switches. So now to open the relay switch, we need to supply the voltage to the gate. Now the problem here is that when we open the transistor, the load is going to be on the source side, not on the drain side. So in our previous example, we open the transistor and the source is connected to the ground, while the drain is connected to the load. However, typically in laptops, that switch delivers voltage to the rest of the circuit. It's the initial switch that is controlled by some sophisticated chip, maybe a BQ chip. It will have 2 transistors. It can detect whether one of those transistors is shorted, and if everything is good, it's going to open first transistor, then it's going to open the second transistor. But as we can see over here, the current flowing through our 10K resistor is not 1.2 milliamps as we would expect. 12 volts, 10K, that gives you 1.2 milliamps. And we're seeing that it's roughly 1 milliamp, a little over 1 milliamp. So what's happening here? The same rule applies to MOSFETs as it does to bipolar transistors. The potential on the gate needs to be in reference to the source. And our source is at roughly 10.3, while our gate is at 12. So a little less than 2 volts on the gate in reference to the source, which means transistor did not open entirely. In this case, what laptops do, the control chip on the laptop, what it does, it actually boosts the voltage in reference to ground to open the transistor completely. We can see that now we have 1.2 milliamps as we expected, but the reason is because we supplied 14.5 volts roughly to the gate while supplying drain with 12 volts. That allows the transistor to open completely. Now in power supplies, we are using transistors as switches, and they cycling, opening and closing at relatively medium frequencies. It could be anywhere from 60 kilohertz to maybe 120, 160. It's going to be always more than 20 kilohertz, and actually roughly more than 40 kilohertz, because if it was lower, it would be audible. We would hear the sounds that are being made by the transformer or other components in the power supply. And if you do hear those sounds, that's most likely a damage to the coils, damage to the transformer. It's not going to be rough. It's probably not going to be a transistor. However, it could happen that one of the transistors is not working, and that's what causes the sounds. But that would also result in voltages not being correct. So that should be easy to find. But you should not hear the transformer actually working, those in power converters that work on 40 and above 40 kilohertz. In power supplies, we have primary and secondary side. Our primary side is on the right. Maybe that's not too intuitive, but well, our primary side is on the right, and our primary side is going to have a hot ground. That ground is going to have to be galvanically insulated from our control side. Our control side is going to have a safe ground. That's going to be pretty much our output. To separate those sides, we typically use transformers, the control transformers, which are much smaller transformers. They don't transmit power. They only transmit the signal from the secondary side with safe ground, with all the logic and everything. And that's how we control the transistor. And as you can see, we are supplying a sine wave. This typically probably would be a square signal, but sine wave works just as well. As we just saw on the previous example, it will result in a square wave on the output, because transistor is going to open and close instantly. What we do is we push the current through primary coil, primary winding of the transistor, of the transformer, and connect the secondary side of the transformer to the transistor, but as you can see, between the gate and the source, allowing transistor to open completely. And we have 1.2 milliamps as we expect, having the load on the source side, right? So it's a high transistor. That's typically what you will see in the power supplies, especially the ATX computer power supplies. On the motherboards, especially on the motherboards, you'll see something like this. You're going to see a coil, in this case L3, and there are going to be two transistors. They could be P channel, N channel, it doesn't really matter. And they're going to open and close. I see I have an error in my schematic, so just don't take this schematic literally. The transistor M8 is not connected correctly. I just noticed that now. That's why, but it doesn't matter. You're gonna have two transistors. They could be two N-channel MOSFETs, because our V10 is going to be a control IC, which has two pins, one for high transistor, one for low transistor. So it's not going to be, the gates are not going to be connected. The only thing connected is going to be a drain and source of the control transistors. But the same way as we did it with the bipolar transistors, the M5 opens, starts charging the coil. As soon as the coil is charged, the M8 opens while M5 closes, discharging the coil. which should result, in this case, in a voltage roughly 1.2 volts. And this would be something you would see on the memory rail of the motherboard. Typically, the memory DDR4 is supplied with 1.2 volts. We can measure the voltage in reality. We can measure the voltage before or after the coil. However, here we see on the simulation that it's not the same, right? Typically it isn't. But in reality, the meter is gonna show you roughly the same thing, whether you measure on this side or the other side. But depending on the circuit, typically there is no resistor outside of the coil. The coil goes directly to the output. There's obviously going to be some capacitance on the output, because otherwise we would have a lot of fluctuation. But the fluctuation, if you check on the oscilloscope, there's always going to be some fluctuation. As you can see here, right, you're always going to see this on the output. This is normal. That's how those converters work. So don't be alarmed when you see something like this. It's wavy, but that's how it's supposed to be. It's not easy to make this a completely flat flat line voltage wise. Now the second example of real world use is the boost converter or step up converter. The previous one was a buck converter or step down converter. This one is a step up converter. It is designed to boost the voltage on the output. And as you can see, the coil is connected to the source V11. And if we remove the transistor M9, the output voltage is going to be input voltage. So this configuration only allows you to boost the voltage. You cannot reduce the voltage. That's why typically when you buy the voltage converters, they're either boost or buck. You typically don't have the ability to both increase the voltage or reduce the voltage. So either they're going to be a limiting or step down converters or step up converters, the boosting converters. In this configuration, what we do is we actually connect, as you can see, we're going roughly to 36 volts. What we do, we just connect the coil to the ground for just a little bit, just enough for the coil to start to charge, and then we stop the flow, the coil discharges, increasing the voltage. For that reason, there's no way to reduce the voltage, because even if we completely remove the transistor, we're gonna have input voltage on the output. The majority of faults on any kind of device, be it the computer, laptop, a motherboard, power supply, the majority of faults will revolve around power. And oftentimes, the reason the power is not being delivered is because of MOSFETs. MOSFETs either are not being controlled correctly, the control circuit is damaged, is faulty, or the MOSFET itself is faulty. The main reason for that is because, first of all, transistors are not going to be we want to use in any kind of circuit, we want to use the cheapest part possible. So oftentimes we operate maybe on say 20 volts. Our transistor is going to be rated for 30 volts, which means any spike above any spike of 10 volts above the rated voltage, or 10 volts above the nominal voltage that we expect, is going to cause the MOSFET to break. The gate can only be charged to a certain level. If we exceed that level, again, the transistor is going to become a wire. That is very often the case in all kinds of electronics. So the good understanding of the MOSFETs is relatively important. However, as you can see, we're not analyzing how MOSFETs work. We analyze how they actually behave in the circuit. I think that method of learning is a lot easier than bombarding you with equations and the diagrams of how MOSFETs are built and how they work under the hood. Finding shorted MOSFETs in the circuit could be challenging because, as we can see, the MOSFET is going to have a very minimum resistance in the order of milliohms. It could be even less than 1 milliohm, which means if it shorts, it's going to be pretty much a wire, which in turn means that if you inject voltage, that MOSFET might not light up. First of all, it might not light up because the resistance is too low. Something else is going to light up, something on the load side. Second, the MOSFETs are usually controlling coils, which are buck converters, which should produce voltage of, say, from 5 volts to 1.2 volts, using the example of the memory on the motherboard. If that be the case, you will not see anything on the thermal camera if you supply 1.2 volts. So you might be tempted to supply 5 volts, because that's what the rail is. You supply 5 volts, and that 5 volts is going to go to the places where 1.2 volts is expected. And that's going to result in further damage. So sometimes finding a shorted transistor, which is MOSFET, is very challenging. So you need to be careful about that, and you need to understand that the MOSFET is that using a thermal camera and voltage injection is only going to show you components that have higher resistance, because they are gonna produce more heat than the ones that have next to no resistance. The MOSFET, the shorted MOSFET, is always going to show up on the multimeter as a short, and it's going to be roughly 0 ohms, or at least the meter is going to show you 0 ohms. You can use milliohm meter to see the actual resistance, and that resistance might be 10 milliohms, 80 milliohms. Some transistors even have 5, 6, 700 milliohms, and those are usually transistors that are rated for much higher voltage. And that is usually how it works. If the transistor is rated for higher voltage, it's going to have higher resistance than the MOSFETs rated for lower voltage. The most important thing to remember about the MOSFETs is that you can break it by just touching it. The most important thing to remember about MOSFETs, which makes them very much different from the bipolar transistor, is that gate can be charged with just touching it with your finger. Just your electrostatic charge on your fingers can be enough to at least partially open the MOSFET, which means if you're measuring anything on the device that uses MOSFETs, especially that uses MOSFETs as output stage, never touch the base. You can touch the drain, you can touch the source, that is fine, you can measure those, but never measure on the gate. If there is a transistor, if there is a control circuit, just check the voltage going to or the supply voltage, supply power to the control circuit. Do not check whether there is a signal on the output, because first of all, you might not see the signal, because you can see that we only need literally microamps to charge the gate and to discharge the gate. So that signal might not show up on your oscilloscope, and in addition, you might cause the transistor to just fully open for the period of measuring, which will damage the device in a very difficult to examine way. So always remember that when you're fixing the device with MOSFETs, you can cause a lot more damage than there is at the moment you receive the device. We only scratched the surface of the MOSFET transistors, but I think that's enough for you to understand how they work, how they're applied in the circuit, and what not to do, which is more important than what to do. To find shorted transistors, always turn off the device, make sure it's discharged. If it has large capacitors, discharge the capacitors, make sure that the device is completely disconnected, because in that case, if you open the transistor, nothing's going to happen. The beeper on the multimeter is a good tool to find shorted transistors, but again, remember that if the gate is charged, the charge on the gate will remain unless there is a circuit that discharges the gate passively. Perhaps a resistor connected to the gate that will discharge the gate. It could be, but remember that oftentimes, at least in my experience, you find a shorted MOSFET, it beeps, you connect to drain and source, it beeps, you remove the MOSFET, and the MOSFET is no longer shorted after removal. But you go to the board and you check where it was between gate and source, and there's no short. So you remove the transistor, the short is gone, but you test the transistor and transistor is not shorted. That can happen. That means that the gate was shorted when you were measuring. The gate was charged when you were measuring. And it doesn't take much. It can be depending on the transistor. This one that we analyzed needs only roughly around 2 volts, 2.5 volts to fully open. Some might require even 800 millivolts, and that potential can remain on the gate when you measure the transistor. So always be aware of that. If you're not sure whether the transistor is shorted, you can take the resistor and actually, if the device is turned off, you can just literally create a short between the gate and the ground to make sure that it's just discharged, and then measure drain and source again. That could save you a lot of time. I know it would if I knew that back in the day. And with that, we're gonna finish this lesson. Thank you guys very much for watching. I do appreciate you, and I hope you learned something useful today. I shall see you guys in the next one.